Well, this is 8:36. Sorry, I'm 6 minutes late getting started. I was grading papers, waiting for someone to come in, and lost track of time. Suddenly looked, and it was 8:32, so I had to run down to the restroom and clear my head one last time. And still nobody's here, so I guess we're going to get started. I'd normally ask if there are any questions. I do have, well, I'll wait till some people get here to make whatever announcements there'll be, because I don't know if anyone will hear this in time for that to make any difference. So anyway, let's get started with where we left off before. Okay, I hope it'll start from there. Well, not doing anything. There we go. All right. My mark was that we had started in Chapter 2, First Order Differential Equations, Section 2.2. We just got started last time and got maybe a page covered there, and we're at the top of page 48. Okay. Now, where we had left off, okay, I guess it was here. For some reason, my slide is doing all sorts of weird things on me. Okay, we had just finished that sort of a mini example. It wasn't called an example, but it was the top of the page. And then somewhere in here, I guess referring back to the definition, and I'll write that down. Let me get my pen set up. Okay. From your definition, if you have a differential equation, dy dx, first order ordinary differential equation, and that you can separate the g of x from the h of y, then you call this a separable thing. Now, when I say separate, that means separable by multiplication or division. You can't add or subtract is not separating, okay, but multiplication and division is. This is said to be separable, okay? Now, it says, observe that by dividing the function by the function h of y, so let's divide both sides by h of y, okay? And divide this by h of y. Now they go through some sort of strange gyrations here. The h of y disappears, and this gives you 1 over h of y times dy dx is equal to g of x. Okay? Now they go through all sorts of bizarre things here. Then they call this one p of y. Now I see no real reason to, but they call it p of y times dy dx is equal to g of x. Okay? Fine to call it that. You can call it whatever you want to. Okay? Where the 1 over h of y is your p of y. Okay? Now, and they do some other strange things here and say, well, if this p of y happens to be 1, then you just have an ordinary differential equation, dy dx is equal to g of x. Okay? Now, I don't know why you would say that would be the case, and p of y would be equal to 1 when h of y is equal to 1, so why in the world would you do that? But now, what if the y was some phi of x? And I mean, for the life of me, I see no reason to make this seem so complicated here. That they're going through all these ramifications here. And they get to the point of some h of y is equal to some g of x plus c, which of course is where we're heading. The equation 4 indicates, and that's that equation, that the procedure for solving differential equation, a one parameter family of solutions usually given by this, okay? And, okay, finally, method of solution. I don't know why they went through all that, okay? It seemed like it was only designed to make it more complicated. Here's what you do, okay? Forget all that, okay? Here's what you do. dy dx is equal to g of x times h of x, okay? I'm sorry, h of y, okay? And just like they said, but let's do it at one step. Number one, we're going to write it in differential. In fact, let's do two steps. Write it in differential form. That would be dy is equal to g of x times h of y dx. All you did was write it in differential form. Write the derivative as a differential. Now divide both sides by h of y. Okay? The h of y's go out, and what you have now is dy over h of y is equal to g of x times dx. Okay? And once you have this done, integrate both sides. Okay? And if you can integrate the left-hand side, okay, we have no idea what the h of y is, but if it is integrable as a reciprocal function, if that is integrable, and to be integrable, of course, you would need to be continuous over the domain, smooth and continuous. Let's just do it that way. And if that's the case, and you can integrate it, and then this is what they call h of y, the antiderivative of 1 over h of y, and this would be g of x, the antiderivative of g of x, d of x, little g of x, and then add your constant of integration. Okay? I do not know, and I mean, you could write a constant of integration on both sides, but why? You're going to just combine them to one. So you only need one constant of integration. Okay? So, all their other stuff there, I have tried to figure out why in the world they would ever do that. Okay? What they do, they change the h to a p, then they supposing a solution is a phi, and then they take a derivative. I mean, it just does all sorts of gyrations that come down to this, okay? Just comes down to that. Why go through the gyrations? It's pretty simple to do, okay? Sorry about that. I've tried to figure out why the book did it, and I, for the life of me, can't. So let's just go with it. Let's do example 1. Here's a differential equation. 1 plus x dy minus y dx is equal to 0. Now this is already in a differential form, which is really good for integrating. Okay? So let's get, first step, separate the d's, okay? But dy on one side, dx on the other, and that's pretty easily done by just adding y dx to both sides. Okay? Now you get 1 plus x dy is equal to y dx. Okay? Now is where you separate your variables. This term right here has only x's in it, but it's with the dy. This term has only y in it, but it's with the dx. So let's divide both sides by 1 plus x. okay? But also divide both sides by y, okay? The 1 plus x's go out here, the y's go out here, and that leaves us with the differential equation dy over y is equal to dx over, let's just do 1 plus x. You don't need to put parentheses, okay? Now, integrate both sides, okay? Well, this is simply log y, and this is simply log of 1 plus x. Now, technically, you should put absolute value bars around those because we have no idea what's the domains of the x's, the ranges of the y. We don't have no idea if they can ever be negative. You can't take the logs of them. You can't take the log of 0, so they can't be 0, but here's something pretty obvious. If y was 0, this is a fairly meaningless equation to begin with. 1 plus x dy is equal to 0. Okay, so what, you know? And if 1 plus x was equal to 0, that's, again, a meaningless equation because you have 0 is equal to y dx. Well, that doesn't produce anything. So we'll assume they're not equal to 0, and the absolute value bars keep them from being negative. Okay, now, you got to put a plus c in here, but before I do that, I'm going to write it as plus the log of c. That's a constant too, right? We're just going to write it as a log, okay? And we'll assume that it's a positive value that you could take a log of. If you want to put it in absolute value bars, you could, but you get to choose it, you know, so choose one that makes sense, okay? Now, what we're going to do here is, because this is the sum of two logs, that's the same as the log of the product, c times absolute value 1 plus x. Okay, I don't know if you remember that from your things, but the sum of two logs is the log of the product. Okay, now that we got that done, take an e of both sides. Okay, now e log y is just going to be y. And e log c, that will be c times 1 plus x. And at this point, we really don't care whether they're plus or minus, you know. There it is. There is your solution, your one-parameter system of equations, okay? Now, they go through, again, all kinds of ramifications to get there, but that, to me, is a simple way to do it. So you get y is equal to c times 1 plus x. Okay? Now, they give a little justification of why you can leave off the absolute value bars, because once you introduce the e's, then whatever the sign of the 1 plus x would be, it still comes out the same. Okay? So, we can just eliminate that, and once you take the e's, then you can forget about the absolute value, because exponentials are defined everywhere. Okay, now, it's not wrong if you just put a c there, but then you can't take the e of both sides. So the advantage of putting the log c is now you can use the property of logarithm, combine those two terms on the right-hand side, and, like we did, and then you can take the e of both sides, and it gives you a lot cleaner solution, okay? An empirical solution, explicit solution, rather than one that has logs in it. Okay, now, let's move on to example 2. Okay? I wish somebody were here. I'd ask if there were any questions, but there's no one here, so let's just move on. Here we have an initial value problem. So this is going to, you'll evaluate what that c will be. So here's your initial value problem, dy dx, okay, is equal to minus x over y. Okay? That's your differential equation, first order, not quite obviously linear yet, but we will make it so. Ordinary differential equation. Here's your initial condition. Y when x is 4 is equal to, the y would be -3. Okay? So not initial in the sense that x equals 0. It's just that we know some value. When x equals 4, y is equal to -3. So there's your some value, okay? You can call it initial value if you want to. So how do we proceed here? Well, again, I would suggest writing in differential form. dy is equal to minus x over y dx, okay? Well, now you got x's together, and if you just multiply both sides of the equation by y, you will get the y's together too. Okay? Here the y's go out, and now you have y dy is equal to minus x dx. Okay? So, let's integrate both sides. I'm going to bring the minus sign out front, and this will be y squared over 2 is equal to minus x squared over 2 plus some constant c. Okay? Now, just to make it a little handier, let's just call it c over 2. Okay, that's just a constant 2, isn't it? And this way we can just multiply everything on both sides by 2 and get rid of our 2's. Okay? Just a little trick. Okay? So this gives you y squared is equal to c minus x squared. Okay? There is your solution. You don't need to take it down to square roots. I don't believe. Let's just leave it like that for right now. Now let's plug in our initial condition. When x equals 4, this will be y squared is equal to c minus 16. Right? That's a really, yeah, okay. C minus 16. Y then is -3, so that would give you 9 is equal to c minus 16. And if you add 16 to both sides, you get c is equal to 25. Okay? Well, plug that back in here, and you get y squared is equal to 25 minus x squared. Okay? Now that to me is a perfectly fine answer. If you want it explicitly, then you'd have to take a square root. Then you have to include plus or minus values. But what is this? If you added x squared to both sides, you get x squared plus y squared is equal to 25. That's a circle of radius 5. So your solution curve would be, that's an ugly circle, isn't it? That circle, okay. With C, you could have a circle of 1, 2, 3, 4, whatever, but this is our solution. Because when x is equal to 4, 1, 2, 3, 4, you're down here at -3. There's your point of contact, okay? Now, if you wanted a functional answer, then you can do this. Y is equal to minus the square root of 25 minus x squared. There you would take the minus value because that is the value of y that gives you that initial condition. So then you sort of ignore the top half. If you want a functional solution, that would be it. Y is equal to minus the square root of 25 minus x squared. Okay? And that sort of defines everything for you. Now, one other thing they do, they put open circles there. Why that? Because there your dy dx would be a vertical line. and that wouldn't be defined by that. Y can't be 0. If we had noticed that at the very beginning, y cannot equal 0. So these 2 points here where y is equal to 0 are out of the question whatsoever. So here is the curve that you have. They did it in the book as green, so I'll do it green. Here's your solution curve, sort of, something like that. The semicircle on the bottom side, because your point 4, -3 is on that curve. It's not on the top part of the curve. And you have open circles at the endpoints because y cannot equal 0 from your initial expression of the thing. Y can't be 0. So you have open circles there. And you choose only the bottom half. Okay? So that's probably not done as smoothly as the book did, but it's fine. Okay? Now, I wish there were questions, but I would answer them, but I can't tell if I'm making this clear or not because nobody's here. Okay, so let's erase that and move to example 3. Here it says solve. Let's go back to dark, back to black. Okay, dy dx, ordinary first order differential equation is equal to y squared minus 4. Guess what? This one's not linear. Okay, we can tell that right off the top. Okay, now, again, if you write this in differential form, you have dy is equal to y squared minus 4 dx. Divide both sides to separate the variables by y squared minus 4. Y squared minus 4. Okay? Now, these go out here, so you have dy over y squared minus 4 is equal to...
Sorry.
Ah!
I left the garage door open last night.
What's that?
I left my garage door open last night.
Oh.
In the rain. We have a low level in our garage, so rain came in. Had to try that out.
Oh.
Mildew.
Yeah, I had a busy morning. Huh?
So that's why I'm sorry.
Okay, inexcusable. Okay. You get fired. Okay. Lose 15 points on the final grade.
I was like, man, he's going to be mad.
Oh, yes, I'm
Man,
down.
we're waiting 20 minutes.
Actually, I can go much faster. I didn't say that, did I? All right. All right. I'll wait for the slide to come up. I've already gotten started and done close to 2 pages in the text, so you'll have to go back and review that. But before we go any further,
Recording?
yeah, I've been recording it. Yeah, can't see it right there. The light's just coming on. Now, I don't know what happened. Okay, you know, last Thursday I had the eye surgery.
Yes, sir. I was going to ask you how you doing about that.
It went well, really well. But now I have to wear reading glasses because they put a lens in that was sort of halfway between reading and computer screen. So I could sort of do both of them. They couldn't put a lens in that would be both because it's only one lens. This lens that I had put in earlier is a distance lens, so that I've got distance vision. But I did this eye I was using for close vision when I could adjust the lens, the original lens, but it had cataract, so it was getting harder to see. So they put the lens in. And now reading is fuzzy unless I have reading glasses on. So since I'm reading the book, you look fuzzy now because if I take, oh, you're better fuzzy. No, I'm just kidding. Okay. But so I'm getting used to going back and forth and either leaving them all or taking them off or whatever. And they said it'll probably take about a month for your eye to adjust anyway, and it may get so I don't need them anymore. I don't know. We'll see what happens. Okay. But I did want to say this. I don't know if you were planning to come by for anything during office hours today. You don't normally have office hours from 10:45 until 4:30-ish, okay, when I have to leave to go to the Birmingham East Campus for a physics class. But Today I've got a doctor's appointment with the eye guy, but he's right across the street here at UAB West.
Oh, yeah.
So all I have to do is go across the street. And I don't know how long it'll take, though. If he's going to dilate the eyes and do all this kind of stuff, that may take a while. If he's just going to examine and see how the surgery looks, then that may not take long at all. I just don't know. So anyway, that appointment is at 2:10, so I'll probably leave here maybe 1:45, because I'll probably just walk over there because there's no reason to drive, and unless it's raining. What's that? I could, but I'll allow myself time, so I'll wait till the stoplight, okay? But I'll make sure you're not on the road. Okay. All right. And I don't know what time I'll be back. I'm going to guess an hour. So between 2 and 3, don't expect to find me on campus. Probably leave a little before 2. I may not be back until after 3, but in that time frame, I probably will not be here. Okay. Now, another thing, they did ask for, it was due yesterday, but I did it over the weekend when I finally could get glasses and stuff like this and see, sort of. And by the way, I thought, boy, I got a long weekend, I'll get a lot of stuff done. It didn't happen that way. Number one, on Thursday, I basically slept most of the day. The anesthesia they gave me for that, it just kept me groggy, and my wife was putting drops in my eyes 4 times a day, and 3 different drops, and you had to separate them by 3 to 5 minutes. I'm still doing that. But every time I lay down for her to do it, I'd basically fall back to sleep. Okay, so it was a good, restful day. I'll put it that way. Then Friday, this eye was still dilated, basically all day long. Finally, at the end of the day, it had gone down. But so I had to wear shades inside for 2 days, even when I slept. But that was fine because I really needed protection anyway. So the second day I couldn't do anything. I couldn't really read. I couldn't do the computer stuff. I couldn't do anything because my eye was still dilated and I couldn't focus. I didn't have the glasses in, just the shades. So then toward the end of the day, though, my wife found some old reading glasses of hers that were not very strong. And when I used those, I could read better. So I started being able to read a little bit, but that was right at the end of the day. So the next day, Saturday, we went out and did some things, and we went by CVS, and that's where I got the reading glasses. And so then I could do some more stuff. But so I got some work done, some on Saturday, a little on Sunday. So I didn't get nearly as much done as I intended. But anyway, that's water under the bridge or over to them or wherever. To grandmother's house we go. All right, we're on page 49. Example 3 at the bottom of the page. I've got it set up here. Now let me go back through the procedure for doing separable equations. Here was the differential equation. Okay? It's ordinary, first order, not linear, differential equation. Okay? Not that that matters too much. And what I like to do first is write it in differential form. So pull the dx over there. Now we got y's here, x is here. Divide both sides by this expression in y. Okay? Y squared minus 4 on both sides. And now we've got a separated, so separable differential equation. At this point, we integrate both sides. Okay?
Did you move the y squared to put it under the dy? They have the same terms, I guess.
Okay, just the y squared without the minus 4?
Like if it was the x squared minus 4, would
you would have left it right over there with the x. Okay? And then y would have been by itself, then you integrate there. You get them separated, then you integrate. Okay? Good point. Okay? However, this is not, the right-hand side I think even I can do, okay? The left-hand side is going to take a little more work. Do you remember how you would approach that integral?
Yes.
How?
It is partial decomposition.
Absolutely. Sometimes called partial fractions. So I would write that as dy over what? Got it. Okay. And this is simply, I go on and do the integral x. Okay, that's it. Now it's going to have a plus c after a while, but let's not worry with the plus c yet.
Oh, you did the integral of that.
Yeah.
Dx. Okay.
Antiderivative of dx is x. Okay, or 1 dx is x. Okay, now, how do we do this? Well, we have this fractional form, okay, that is 1 over y minus 2 times y plus 2, okay? And we want to write this, okay, is this how you did it? A over y minus 2 plus b over y plus 2. Okay, now, at this point, there's a little trick. Oh, no, okay, let's first do multiply both sides of the equation by your least common denominator. So you don't have any more denominators. I don't like denominators, do you? Okay, let's just get rid of them. So multiply this by y minus 2 times y plus 2. But you might have to multiply this by y minus 2 times y plus 2. But you have to multiply this by y minus 2 times y plus 2. Okay, here your entire denominator goes away and all you're left with is 1. Here the y minus 2 goes out and you have a times y plus 2 plus the y plus 2's go out here. They've been dating, okay. B times y minus 2. Okay. At this point, there's a little trick you can do. And it always sort of bugs me that it works, but it does. Okay? This should be true for any y's, right? They say. So let's just choose y equal some value. I'm going to choose y equal 2. Why? This term goes to 0, right? And if you choose y equal 2, then your equation here is 1 is equal to a times 4. Exactly. So a is equal to 1 over 4. Got it. Okay. Now we're going to do the same thing, only different. Choose y equal negative 2. That will wipe out your denominator over here on this side, right? I mean your term on this side, the a term. Y is equal to negative 2. This would go away, and you have b, 1 is equal to b times negative 4. So b is equal to negative 1 over 4. Okay, so now we go back to this form up here, and so this is now 1 over 4 times y minus 2, because that's your a, 1/4, minus 1 over 4 times y plus 2. That's what your integrand is going to be now. Once you split it into this, you get that. So,
but those ain't the same.
What's that?
Those wouldn't be the same denominator, would it?
This is 4 times y minus 2 that y plus 2.
So
It's not the same denominator.
It's not the same denominator, so you can't combine them.
Okay, if you combine them, you're going to get back here, and that's what you're trying to get away from.
Oh, sorry.
Okay, right? Okay, so this is how we want it to look. Because at this point, let's rewrite this. I don't have a lot of room.
You can erase.
Okay, I can erase all this stuff at the bottom.
Yes, sir.
Okay, so let me do that. We've already done it. Been there, bought a t-shirt, all that kind of stuff. So. Okay. I'm going to leave that because that was my result. Okay. That's what, I should have left something there to tell what that was equal to, but that, okay. Okay, let me go back. Okay. going to try to atone for my errors. Okay, that denominator is that. Okay, what we did there was get that, break that. What did you call it? Decomposition? Partial decomposition. Okay, so now your integrals are this. The integral, I'm going to pull out the 1/4. Okay, you got dy over y minus 2 minus, pull out this 1/4 and do y plus 2, okay? dy over y plus 2. And that's equal to your x. And we may have a plus c somewhere in there in a little bit, but we'll come back to that later. What's that going to do? What's that? Antiderivative of 1 over y minus.
That's just going to be the natural log.
Absolutely. So this is going to be 1/4 the natural log of, and you need to put absolute value bars, y minus 2, because it can't take the log of a negative number. Now a little bit of a timeout here. You can't take the log of 0 either. But guess what? This can't be 0 because that would be illegal. This would be illegal, you know, because if this were 0, y is equal to 2. Okay? If that were 0, y is equal to 2. If y is equal to 2, that's 0. Your whole problem. That would be dy dx equals 0. What an exciting differential equation that is. That could be anything. So y is not equal to plus or minus 2. So we can get away with this. And this will be minus 1/4 log of, again, absolute value bars, y plus 2. And this is equal to, I'm sorry, keep wanting to put my c in there. Yeah. Yeah. But I'm going to put, for right now, x. Okay, just x. Now, it's going to have a c in it, okay? The question is, how do you want the constant to be? This is where it gets a little murky because you have to sort of look ahead and see what you want. Well, I'm going to do a couple things to it first to give me hints. First, I'm going to, from the rule of logarithms, that a times the log of something is the same as the log of this thing raised to the 8th power. You remember that? Okay. It's a rule of logarithms. A log b is equal to log of b raised to the 8th power. You remember that? Don't. Okay.
Don't?
Huh?
Don't remember it?
That's what I'm asking. You don't remember. Is that right?
Yes, sir.
Okay. Let me see if it's anywhere in your book here. Let me write down several. I'm trying to.
A be the 1/4?
Yes, exactly. Okay. Let me see if I don't think this book has those kind of tables in it. So let me. Let's see.
Is that going back to the rule of log, like when we did
Okay.
we did like logarithms in general?
Okay. Here's where it's going back to. Okay. Do you remember this one? That log, can I use A and B indiscriminately here? Log A plus log B, maybe I should have done it this way. Log of A times B is equal to log A plus log B. Does that make sense? That is a rule you remember of logarithms. And log of a quotient is the difference of the logs. Log of A over B is equal to log A minus log B. Remember that one? Or I can sell it to you. I can convince you it's true. tell you it's a wonderful thing, right? It is. It's the rule of logarithm. You never used a slide rule, did you? You don't even know what one is, do you? Okay. Back before calculators, and there was a time before calculators, okay? I was in college at that time. The first calculator I ever saw was my sophomore year, first quarter, sophomore year, physics class. Big, huge lecture room, about 200 students in it. I went to Georgia Tech. Everybody took physics.
Oh, yeah.
Yeah. So, big, huge lecture room, and in walked two guys with these calculators. I had read about calculators. I had heard about calculators. Two of these calculators strapped to the belts. That's how they used to do them. Because the rest of us were wearing our slide rules strapped to our belts. Okay, we were really nerdy, you know. But anyway, in walked these two guys with these calculators. And all the rest of us gave a unified sigh saying, there goes the curve. Okay, because these guys are just going to be able to punch it in their calculators and come up with answers where we were having to slide the logarithm around, the slide rule around and just getting approximate answers. So we thought, there goes the curve. Okay. Now those calculators, I didn't own one then. I couldn't afford one. They could add, subtract, multiply, and divide. And they cost about $400.
How big were they?
Huge. They were thicker than this, wider than that. They were almost the thickness, the width of these two put together, and about down to there. Not quite as long as that, and they were as thick as this one. And you had to plug them in. Okay?
This one was just big.
Okay. It was about that size, a little thicker, but it had to be plugged in. Yes. And it could add, subtract, multiply, and divide.
And that's it?
And that's it.
Oh.
For $400.
$400 for a basic, and you can go to like Walmart and get one for like $5.
They will give you freebies at some tables, you know.
Yeah.
You know, they give them away, you know. Not at Walmart, but if you
like here or like
an AEA table.
Yeah.
They gave me a calculator. We do that, and it's about that thick and about this. It's just tiny. Huh? Solar power, everything, and it's worked for years without ever. It doesn't even have a plug. There's no way you could plug it in. So, at a very different time. Okay. So back before calculators, there were slide rules, and what slide rules enabled you to do, you had to keep up with the exponents. When you're multiplying huge numbers, you could basically pick out close to, thinking in scientific notation, maybe 3 significant digits. And what it was, a slide rule was a log scale here that was fixed, and up here, you could do a lot of things with it. And then the middle scale was slide, that's why it's called a slide rule, and it was also a log scale. So you'd find the number you wanted, okay, slide this to that, multiply it by the number you wanted on there, read here, and then do an antilog, and you would get your answer. Because the log of a product is the sum of the logs. And that's what you do on a log scale. You put the first number in, add it to it, the log of the second number, then undo that, and that would give you the antilog of the product. Okay? That would be the antilog of the product, do the antilog. That would be the log of the product, do an antilog, and that would give you the product. And maybe to 3 digits, and that's all you could get, okay? But that's all we had, okay? And that's how that worked. Basic properties of logarithms. Okay. Now, what if you had log of A times A, not A times B? What would this be? Log of A plus log of A. Right. So this would be 2 times the log of A. But another way you could write this would be the log of A squared. And there we have that the log of A squared is equal to 2 times the log of A. So the log of A to any power is going to be that power times the log of A. And that's exactly what we've done here. We're starting with this side. That's the same as this. So what I'm going to do here is that. I'm going to change this from a product to a power. Okay? It's a long way around to get here. Can I erase a lot of my mess up there?
Yes, sir.
Or you want that anymore? Okay, so let's...
Yeah.
Okay, all right.
I'm almost done. It's going to get ln of a squared.
Oh,
It's good. It's good. I remember that. Ln of a equals...
ln of a squared is equal to 2 times the log of a. There's the end part of it. Is all right?
Yes, sir.
Okay. So that leads to a times the log of b is log of b raised to the a power. Okay. All right, to erase all that? All right. So, going backwards, or based on this one, okay, and you're okay with this. You'll buy that. I sold you some swampland in Florida. Okay. Okay. Now, what's that?
I don't think you lie.
All right. Only if it was lying down. Okay. All right. So what I'll do now, I'll take this one and rewrite it this way. The log of y minus 2 to the 1/4 power minus the log of y plus 2.
So we do ln of a divided by b.
Say again?
So would we do ln of
As that's the next step. You got it. This is equal to x. Now we probably will throw a c in there somewhere, but we'll come back to that. So then this will be the log of,
a divided by b?
yeah, which will be absolute value of y minus 2. And since they're both raised to the 1/4 power, let's just do y plus 2 divided by y plus 2 and just do all of them to the 1/4 power. Okay?
Now why is it raised to the 1/4 power?
Well, you've got it here. You know, these are here. So when you put them over each other, that's the log of this to the 1/4 divided by this to the 1/4, right? Since they're both to the 1/4 power, just put them both together. Okay? And that's equal to your x, right?
I do have a quick question.
Okay.
Instead of like originally having that 1/4, could we just got rid of it by doing instead of like raising this to 1/4 power, could we first have did ln of a?
And make this a 4x over here. Multiply this before, that before, and that before.
I guess we could have
That
done
would be a
before.
perfectly good thing. Is that what you wanted to do?
Well, I mean,
That's legal in most states. Okay.
like we have to address the 1/4 before we do anything.
No, what did you want to do with it?
Could we have done ln of like 1/4 over y minus 2 over ln or over 1/4 y plus 2, and then the 1/4 would have canceled out, right? Equal 1.
Okay. No, okay. You mean take this and divide it by this and divide it by that?
We're moving it to the ln of a over b,
Right.
right? So if you have 1/4 over 1/4, wouldn't that just go to 1?
Okay. Here, if you took this and put it under here, and then you wipe out the 1/4, is that what you're saying?
Will that
Okay,
be-
no, the rule isn't that a constant times log, it's a law. You have to move this here, and you have to move that there before you can use that rule. But I liked your idea you almost had if you just multiplied everything before there.
do that too.
Yeah, and let's do that. That would have made the whole life a lot simpler. Made that 4x. Okay. I like that. So now this would be just the difference of these two, and we don't have to have them raised to a power, and this is equal to 4x. Now we still haven't dealt anything with the c. We really need to, okay? I was sort of putting it off until I had to do something else. And let's make it 4c. That's still a constant, right?
Yes.
Okay. So let's say have this as plus 4c. Okay, and then make this 4 times x plus c. You okay with that?
Yes, sir.
All right. Now, what we want to do is take the e of both sides. And what that e will do then will be wipe out the log, and then you have y minus 2 over y plus 2 is equal to e to the 4 times x plus c.
I do have a question. Why is the c positive on that side?
You can make it anything you want to. I mean, it's a constant. It could be negative, or it could be a negative c. I mean, it's just a constant.
I know, but when we integrated the dx, was that supposed to be x plus c?
It could have been x plus c, it could have been x plus 4c, it could have been x plus e to the c, it could have been x plus log c. You can make it any constant you want it to be.
Okay.
I'm just trying to make it a constant that'll be handy for us.
Yes, sir.
Okay. So that's all I'm doing. And that's where the art comes in. This isn't science, it's just art. Okay? You're trying to get it to work well for you. Okay? Now, what we could do here, and I'm going to, a rule of exponents. And I think you know this one, don't you? Is that that's the same as e to the 4 times e to the x plus c?
Yes.
Okay. Well, this is just a constant. So let's make that, no, let's, that 4, well, we'll leave e to the 4 for now, okay? Now, I'm rapidly running out of room. So let me go and erase some more.
So wait, what are you doing for the, why is the e to the 4 go away?
Well, no, I was going to make it a constant, so,
Oh, like
yeah.
its value?
Yeah. No, I'm going to leave it there. I had started to make it a constant, and I thought, let's not do that yet. Okay, so let's, because it's a specific constant. It's not just any old constant. It's e to the 4. So let's leave it like that. Okay.
This is not hard at all. Or not hard, it's
Well, it's just long and nasty. Okay. Right. I'm having to use a lot of screen. Okay. So what we're going to do now is multiply both sides by y plus 2. So now we have a y minus 2 is equal to e to the 4th times e to the x plus c. I may want to put them back together, times y to the minus 2. Right?
Yes.
Okay. Now, I think I've sort of screwed something up somewhere and probably could make it, oh, whoop, that's a plus 2. You said yes, and it was wrong. Okay.
Hey, I was just going with you.
Hey, that's not the question. I mean, I asked you if it was right, and you said yes. No, okay. You failed, okay, in your job, okay? You're supposed to correct me when I'm wrong. Okay. Nicely, okay.
I didn't know you.
Huh?
I didn't want to know you.
Oh, I see. Okay. So this would then be e to the 4, e to the x plus c, times y plus 2 times e to the 4, e to the x plus c. Okay?
What did you do?
We just distributed this thing with the y, and this thing with the 2. So we have the 2 with the y and have it with the 2. E to the 4 times that, e to the 4 times that.
Is there, how come the y is not connected?
It's I put parentheses there so hopefully to make it look clearer. Maybe if I put it here. Yeah. Okay. Would that be better?
Yes, sir.
Okay. It'd be wonderful that way. Okay. Now, what we have is a term with y in it here and a term with y here. So let's also add 2 to both sides. Okay, so get rid of this. Okay. Now let's subtract this one, minus y times e to the 4th e to the x plus c from both sides. Okay. So this goes out there. We've already added the 2. So what do we have now? Let me erase this at the bottom. Hopefully I won't need it. If I do, that's too bad. You'll have to get it from your notes. The differential equation part is easy. It's all this manipulation that just gets really messy. Let's factor out a y. Y times 1 minus y e to the 4th. No, factoring out the y. Sorry. 1 minus e to the 4th e to the x plus c is equal to, and what we had left over here was just 2e, and we're actually going to factor out the 2. 2 times e to the 4th e to the x plus c. Okay? Those both had 2's in them. So what we're going to do now is divide both sides by...
Can you explain? Sorry,
Oh, wait.
Why is it 1 minus?
Okay, just a minute. I messed up here. This is 2 times 1 plus. Okay. Now, what's your question?
So why is there 1? I'm lost. Sorry.
Okay. Did you have it that we had the y minus 2 is equal to this stuff?
Yes.
Right? So this term had a y in it. So I added this, subtracted this from both sides to get my y's together. I added 2's to get the terms without y's in it on the other side. Okay. So now we have a y times 1 minus this thing here. And over here we have a 2 with this plus 1 plus that on this side. Okay? Now what I'm going to do is divide by this.
Why does it become a 1? 1 minus.
Okay, because you had a y minus y times this. So that would be factor out a y, and you're left with 1 here minus this thing here. Factored out the y. Just like we factored out the 2 here, and left with this plus 1. 2 times this thing plus 1. Here we factored out the y and had 1 minus this thing here. It's magic. To answer your question, it was magic. Okay. Now, this isn't going to be quite as pretty as the book has, but it's going to be close. 1 minus e to the 4th e to the x plus c. That's going to disappear, and here you have a 1 minus e to the 4th e to the x plus c. Now, to answer your question, why were we doing that? To isolate the y, so we could find an explicit solution of y. And here it is. Okay? Now, that's not quite the form they're going to have their answer in. Okay?
And you pulled the 2 out, right?
Yeah. Now, yes, I pulled the 2 out on that side. Now, here's where the magic comes in, okay? To get it to look like that in the book. Let's look at this e to the 4, e to the x plus c, okay? That's the same as e to the 4, e to the x, e to the c, isn't it? No, I did something wrong before, and you agreed with me, and you shouldn't have. No, that's fine.
Don't be accusing me of getting crimes.
I think I made a... Let's see if that works. No. here's what I should have done. Here at this step, okay, let me back off a little bit here. I'm going to have to do a bunch of erasing, but I'm going to try to minimize it. Back at this step, when I said this and you said that was right, here's what I should have done. Rather than that, I should have done this. And this is my bad. This is e to the 4x plus 4c. I just distributed that, right?
Oh, and you should have done.
Now I do e to the 4x times e to the 4c. That's where I should have done that. This is just a constant, okay, which will make c, okay? So everywhere I have that mess, let me write e to the 4c. So let me here and here, because that's where I made the blunder, okay? This is c e to the 4x, and this is c e to the 4x. Now we have our answer just like theirs. Sorry about that. That's made the mistake there. Okay. Now what we have here is y is equal to 2 times this thing over this thing. There's a one parameter system. Weird looking, but still doable. Okay. And give me an x, any x, plug it in, you can get your y. Okay. So that's how they got the answer. It's not an intuitively obvious situation. Okay. It's pretty esoteric, okay? But that's exactly the answer they have there. I just messed it up over there with that. All right. Now, at least I've been going at it for an hour and 15 minutes, and we have left to go about an hour, right? For class. Would you mind taking a break?
That's fine.
Okay, you want me to leave this up so you can fiddle with it?
Yes, sir.
Okay.
Please leave it up.
All right. Then I'm going to go. I've got to have a bladder break. Yeah. Second? Oh, pause. Okay, yeah. Sorry. Okay. On the test, number one can just be done fairly simply, but show your work if there's got any work to be done. Number two, there's no way you can do it without showing an awful lot of work, okay? So you're going to need, I don't think even the back of the test, that would be fine to write on, but you're not going to be able to get everything on there, okay? Number three is really easy, and you can just write down the answers, or you can write down a little bit of justification if you wanted to. Number four, notice it says verify. That means there's a lot of work to be shown, okay? Number five, that could probably be done fairly shortly, but you got some work to show. Number 6 and 7 are both verify. So there's a lot of work to be shown there, okay, on both of those. Number 8, verify. That's going to be a lot of work to show that. And number 9, find the solution. There is going to be a fair amount of work to be shown there. Here's the deal. I think I addressed this earlier, maybe you were here the day I did. I've received a certain amount of guff from some of the other instructors because I give take-home tests. And the reason I do, I really can't feel like I can test the material adequately unless I give you time to do it, okay? And one class time is just not really going to be time enough to do it. So anyway, so therefore I have to require you show your work. If you just give me answers, certainly with the verification, the verification is the process. It's not that there's an answer. It's already told you what the answer is, okay? How do you get that answer? How do you show that these are true, okay? And even things like number 9 and some of the others that, you know, find the solution, I need to see how you got it. If you just write down a solution, I don't know where you got it, so you can't get more than half the value of the question. If you get the right solution, you get half the credit. But that's all, okay? I have to see the work to get full credit, okay? So, in other words, plan to attach several pieces of paper would be my guess, Okay, I can't imagine it without it. The one that's been turned in had several pieces of paper. Okay. All right. We had just finished example 4, wasn't that? No. This was example 3. Example 3, bottom of page 49, top of page 50. Okay. We're getting ready to start example 4. Have y'all got what you need on this one?
Yes, sir.
Okay. It's messy, and I've had to do a lot of erasing, so you won't be able to piece together. But if you go back and look at it, you'll see all of it. And it'll still be messy, though. But you'll see what I erased and what didn't. So here is an initial value problem. Okay? Solve this. E to the 2y minus y cosine x dy dx is equal to, at first e to the 2y minus y has to be in parentheses, is equal to e to the y sine of 2x. Got it. There's your differential equation. It's an ordinary, first order differential equation, nowhere close to being linear, okay? No way you could even construe that to be linear. You have e to the 2y's, e to the y, yeah, no way that could be linear. But it doesn't matter, it's just an equation. Well, the sines and cosines all are dealing with x, and the function of x can be anything. It's the y's that determine the linearity, okay, or whatever the dependent variable is. That's what determines linearity. Now, it's an initial value problem, and this one is our good old favorite, y of 0 is equal to 0. In other words, when x equals 0, y is equal to 0. That sounds like an initial condition to me. Okay. Now, they were very nice to you, whether you believe it or not, in that they've already separated this from this. These are all y's, that's all x. If they had really wanted to be nasty about it, they could have said this is, in parentheses, cosine x e to the 2y minus y cosine x, in parentheses comes this and this. Then you'd have to separate these. But they've already separated this for you. Here's your y's, there are the x's. And they separated this for you. There's your y, there's your x's. Okay? So those parts are separated. So the first thing I would do, or what would be the first thing you would do?
Derivative.
Not derivative, write it in differential form. Okay? In other words, write this as e to the 2y minus y cosine x dy is equal to e to the y sine 2x dx. That's written in differential form. Now, the book doesn't necessarily do this, but to me, this makes it easier to see and understand. Okay? Now, we have your dy here on this side, dx there on that side. So let's get all the y terms with this one and all the x terms over here with the dx. Now, this is a y term that's right where it belongs. Leave it right there. The cosine x needs to be divided away, right? But if you divide it over here, you have to divide it over here too. Okay? But this e to the y is with the x's. We need it out of there. So let's divide it here. Okay? Now these go, those go. Let's see what we've got left. All right. Now, I want us to do a little bit of thinking before we just start writing. Ooh, that's going to hurt, isn't it? Okay. How can we simplify this a little bit?
Could you get rid of e to the y?
Get rid of it? Just throw it away?
Not get rid of it, but like,
Okay.
could it just become e to the 2?
Okay. This is e to the 2y over e to the y, right? Okay. And isn't that, okay, you said e to the 2? Okay. Let's see if that's right. Let's see if that's legal to do in most states. This is,
couldn't you just write it
yeah,
as e to the 2?
yeah, this is the same as e to the y squared. Is that what we're saying? And this is e to the y. So that would be, no, that's not right. Yeah.
Or you could just write it like
Right, right. Okay, yeah. It'd just be e to the y then. That's what I meant to do. Not y. Whoa! Go back. Okay. Get my eraser back. Okay, here we go.
like we did,
Okay, right. I erased the wrong thing again. Okay.
e to the 4
Yeah.
x plus
Yeah.
4c.
And one of those goes out, and you just got e to the y. Okay. I wasn't understanding that what you meant, but okay. So this will be e to the y. And the next term will be minus y e to the minus y. Is that not true? The other way you could think of this is e to the 2y, and this is e to the minus y, e to the 2y times e to the minus y. Add the exponents, you get plus y. So anyway, that part's right, and this part would be that, right? Now this is something I can integrate. I can't integrate it like this, so that's why I was wanting to do this. Okay, so you got that? Okay? So this is your dy term, and over here, is there anything we can do to make that a little nicer? You got a sine 2x and a cosine x. Remember any of your trig identities that might help?
I mean, that could be tan with a 2x.
It could be what? Anyone remember what sine of 2x is? Isn't that 2 times the sine of x times the cosine of x? Okay, he's going to buy it.
1/2.
Okay, no, okay. That's that. Now, right?
Yeah. So
Or is this mystery meat?
you get rid of the cosines.
You can get rid of the cosine. Is that legal? Do you remember that is an identity? Or am I just pulling the wool over your eyes? Okay, pulling the wool. You want to see where that came from, or are you interested? Huh?
Sure.
Okay. Do you remember this? Sine of a plus b. Do you remember how that went? Sine a cosine b plus cosine a sine b. Do you remember that? Or does it sort of strike a...
It's from Cal 2.
that would have been trig. It's been well before Cal 2.
Oh, well, I don't remember trig.
Huh?
I don't remember trig.
Obviously. Okay. No, I mean, okay. No. This is where it comes from. And then if a is equal to b, you got this is 2a, right? And then this would be cosine a plus sine a cosine a. That's 2 sine a cosine a. Or 2 sine a cosine a. So that's where it comes from. So that can be done. All right, so the right-hand side becomes 2 sine x dx. So at this point, we can integrate both sides, right? Oh, I'm going to put the integral 2 outside. Okay. Are you okay with that? All right. The first one here, this is pretty straightforward integration. It's the antiderivative of e to the y. E to the y. I like it. Okay. So I'll try to get it under here. E to the y. Now this next one though is going to require something else. Anyone remember what the technique would be there?
Wait, the second one?
Yeah, this one here.
Oh, what you have to do, integration by parts?
That's it. Perfect. So let me come up here where I did my trig stuff. Erase it if that's okay. I've erased it anyway, whether it's okay or not. Okay? And let's do integration by parts up here. Now, remember there's going to be a minus sign, so I'm going to pull that out. So let's do the integral of y e to the minus y dy. Okay? Now, how does integration by parts go? You remember?
S of u dv equals uv, or uv minus the interval of
VDU.
ddu.
Yeah. Okay? So we need a u.
No, it's vdu.
dv. Yeah, exactly. Okay? So let u equal what? That's the choice. That's where you have to make your decision. What you let to u be u and what you let be dv.
You let u equal y.
Y, perfect. And that makes dv equal e to the minus y dy. Always keep your d's together. Okay. And then what you do next? Then
To take the derivative of y.
du is equal to dy. Again, your d's go together. And you integrate both of these and you get v is equal to
E to the negative y.
e to the minus y with one little exception.
Y in front of it. Negative y?
Negative y. Because you have to unchain rule it, right?
Oh, yeah.
Because take the derivative of this, so you get minus e to the minus y times the minus 1. Right?
Yes, sir.
All right, now I know where your finger was going. Well, I hope I do. You take the two of these. Now remember there was a minus sign down here, but you got a minus sign here. So this is going to be a plus y e to the minus y, right? Then you have a minus. Okay, remember this minus was there. Then you got a minus, and then you got another minus, so that's going to wind up a minus here. 3 minuses will wind up being a minus. Okay, and then you do the bottom line, the integral of the bottom line. That's where you did the bottom there, and that was your
interval of negative e to the negative.
Yeah, but I already pulled out the minus. So e to the minus y dy.
Oh wait, so would the minus turn back to a plus?
Okay, well wait. Okay, you had a minus there to begin with.
Yeah.
And then you have uv minus, so that then takes that to be a plus. And then you have
V.
this, and that has a minus, so that gets it back to being a minus again. But then when you do the integral,
Positive.
you're going to get a minus again, so that's going to be positive. You're right. Surprising. I mean, you're right. Okay. And this is equal to, what's the antiderivative of sine x dx?
Negative cosine.
You got it. So it's minus 2 cosine x. Now we need some c's in there. I don't know where and how to put them yet, but let's remember they are. Okay? Now, can I come up here and do this one again? This now gives us e to the y plus y e to the minus y. And then when you integrate e to the minus y, you get minus e to the minus y. So the minus and minus is plus e to the minus y. And that's equal to minus cosine, minus 2 cosine x. Now, the constant. I think we're just as good off just making it a plus c. You don't need a constant for every one of them. Just put all the constants together and make it plus c. Okay. Now, what's the chance of solving this explicit for y? I don't think it exists, okay? But remember, we have an initial condition here, don't we? So let's plug in 0 for x, and at the same time 0 for y, right? So the first term will be e to the 0 is?
E to the 0 is 1.
1. And then the next term is going to be a 0. Next term is going to be e to the minus 0 is still another. So you get a 1 plus 1. High level math today, okay? And then over here, when x is 0, cosine is what?
Cosine of what is?
Cosine of 0.
Oh, but this is 1.
1, so that's going to be a minus 2 plus c. Okay, so what do we have here? We have 1 plus 1 is 2, so 2 is equal to minus 2 plus c. Guess what c is equal to?
C is equal to 0. C is equal to 4.
It's equal to 4. Is that what you said?
Yes.
All right, so here's our solution. E to the y plus y e to the minus y plus e to the minus y is equal to minus 2 cosine x plus 4. Okay. Now, there may be some ways to clean this up just a little bit. Like you could factor out an e to the minus y from these two terms. And that would be, let's see what that does. It may not do anything. E to the y plus e to the minus y times y plus 1 is equal to minus 2 cosine x plus 4. You could go back and put this e to the minus y in the denominator as e to the y, and then you go back to having e to the 2y plus y plus 1 is equal to minus 2 cosine x plus 4. Now, I can't think of any other way to write it. I don't know if they'll do any of those. Let's see what they got as an answer. They left it in that very first form that we had there, right there. E to the y plus e to the minus y plus e to the, plus y e to the minus y plus e to the minus y is equal to, they put the 4 in front, 4 minus 2 cosine x. Yep, that's what we did. Now, this function here, where you have the plus c in there, okay, this was our general solution without the initial value in it. That comes out being a whole passel of lines like this. And they didn't draw them all, they just do some of them, okay? When y's gets very large, things get closer together, and y's get very small, things get closer together, okay? There's some curvature with the x's, but basically this sort of gets to dominate, okay? When you have x equals 0, y is equal 0, that curve right there is the one that counts, so you put that in. They put c equal to, there's c equal 4, gives you that one. I don't know why they put c equal 2 in there, that's beside the point anyway. But it's just use of computers.
Can you explain the retry factor, not the e minus y?
You mean down here?
Mm-hmm. Yes, sir.
Okay, the book didn't do it, so it's not necessary. But I first factored out the e to the minus y here, right?
So you have
That left us with y plus 1 here, okay? And then I said, well, that e to the minus 1, that would be the same as e to minus y. It would be 1 over e to the y.
Mm-hmm.
So I just did that and put it down here. Well, then, since you have what? I left off my denominator. Okay, sorry. This doesn't make it any better, okay? But then, if you put this over e to the y, that gives you e to the 2y plus this thing all over e to the y is equal to that. It's no better. It's no simpler. I thought maybe there was some way things would get a little simpler. They did. So the book is left. That's just, I was trying to see if there was anything to make the thing look simpler. Okay? And there wasn't. I was also seeing if maybe there was some, by stretch of imagination, a way to isolate the y. There wasn't. Okay? No way. So that was just useless work at the bottom. And left off the denominator at the very bottom. Okay. So anyway, they give use of computers. They have a little blurb there. Since I'm not using them, we'll just leave it alone. Okay. Now, they have a little blurb at the top of page 51 that I'm not absolutely certain if it's worth the effort to spend much time with it. Speaking of which, no, we got another 30 minutes, right? Okay. I looked at the clock and said, hey, we don't have any time, but no, we do. If an initial condition leads to a particular solution by yielding a specific value of the parameter C in a family of solutions for first-order differential equations, there is a natural inclination for most students and instructors to relax and be content. However, a solution to an initial value problem might not be unique. And they showed that in an earlier thing you had two potential solutions. So I don't know for sure why they're running over this again. It seems like we've done that ad nauseum. So I would say let's move on. Now, the next thing almost seems like it's cheating, but it's not. Okay? If you can't do an integration, leave it as an integral. Okay? I can see all of my answers coming out as integrals. That won't work. Okay. What if you had a situation such as this, dy dx is equal to some g of x, really simple separable equation, when y at x0 is equal to y0, initial condition, okay? Defined on, I can't write, on some interval I, okay? What you do, write it in differential form, dy is equal to g of x dx, integrate both sides, and you have y is equal to some, I don't know, maybe I can't integrate x, g of x, maybe it's not integrable. Then you could leave it as
is this the integral defined function you're looking at?
Yeah, integral defined function, that's exactly it. And they just skip steps sort of like crazy here, not showing you how they get it, they just write the answer. And I'll kind of sort of describe that to you a little bit, okay? y is some function of x. We just don't know what it is because we can't do the integral. But we know that when x equals 0, or x equals x0, y is equal to y0, so that's going to show up. Don't worry about that yet. I'll explain it in a minute. Times the integral from x0 to x, and then they put the g of t dt. Now this is sort of going back to the fundamental theorem of calculus part 2, where they express things like this. Now, this is one way to express your solution. If you don't know how to integrate that g of x up here, well, you can change the dummy variable of integration, even though it's the independent variable, make it t rather than x, because you're going to put this in here to make y a function of x. So for any x, you can get a different value here. Now, you might say, where did that come from? Okay? Well, here's where it came from. When x is equal to x0, this integral goes to 0, because then you're integrating from x0 to x0. So that goes to 0, and then that's equal to y0. So that's where that came from. And then you have this as the integral. Okay. Now, doesn't seem like you solved the problem, except, but guess what? Even if that was not an integrable problem, you can still do, you know, go out and purchase, or your company may already have a module that does numerical integration. So then you may have to do it numerically. However you do it, if you can't do it analytically, you're going to have to do it some way, and usually they're available having numerical integration packages. So that's right.
So the answer just be x minus x of 0, or no?
What's that?
Like, if you were gonna, like, I guess, solve, like, that, let's just say that formula that you have there, would it be y of x equals y of 0 plus, like, x in respect? Or how would you do the antiderivative of that g of t?
Okay.
That interval right there.
Yeah.
Like, if you
That's what I'm saying. If you don't know how to integrate this, if it's not an integrable function, leave it in this form and then buy you a package or use a package that does numerical integration. And that's what you have to do. When I was doing my doctoral dissertation, we had, goodness gracious, they were awful functions. And there was no way to do them except numerical integration. So we had this, and I had to write the program for it. My computer science professor helped me clean it up a little bit, but we did it, and it took, to get the precision we needed. I remember I had the flu, and I was just as sick as I've ever been. But I was running a little Apple computer at the foot, not a Macintosh, the old Apple computer at the foot of the bed. I would type in and get it going, and then I'd lay down and rest for about a half hour or so, and it would crank away for a while, and then take longer and longer and longer in between things. Finally, it would stop, and it got within the tolerance. But it was having to do calculations just out of his ears. But it was a slow computer. I'd sometimes be in bed for a half an hour, 45 minutes before it came out with something. I got it, and then enter another one. And that's how I was doing the research that day. I just crawl back in bed and go back to sleep until I thought I heard it quit grinding on the printer. I'd go over and look, and if it was through, then I'd enter the next bit. Okay. So yeah, sometimes you have to do numerical integration. Hopefully you don't have to write your own package in BASIC. Ooh, it was awful. And that took a long time. So that's all they're getting at there. All right, let's do example 5, which unfortunately is probably going to produce something that's similar to that. Let's do this. Solve dy dx is equal to e to the minus x squared. And this is initial condition when y is equal to 3 x is equal to 3, y is equal to 5.
Why do all these problems got E?
They love ease, okay? This one will not be so lovable, though, okay? Well, that's already set up really well for you. All you have to do is write in differential form. dy is equal to e to the minus x squared dx, okay? And here's Carlton. Okay. Wait a minute. I've just been marking y'all for last Thursday. Okay, I hadn't updated this. Today is the 18th, right? I've been putting in the wrong thing. Yeah, I hope that's right. So, Justin's here. Daniel's not here yet. Carl's not here yet. Carlton's here. Nolan's here. I put Nolan in the wrong place anyway, okay? So, Julian's not here yet. Okay. Glad y'all are here. And glad you're here on the right day, too. Okay. Because last Tuesday, about this time, I think I was heading home already. Okay. I had to be there at 5:30 in the morning, and they didn't start the procedures. Sat around for a full hour before they called me in, and went up and laid around for a while and went through all these questions and all kinds of stuff, and finally wheeled me to the place, gave me anesthesia, and then I thought it was the same people and stuff. He said, "Oh no, you're through." Okay, it was over with. And my wife said it couldn't have been more than 30 minutes, out of there. So, and we were heading home probably by this time in the morning. Maybe we were already home. All right. So we weren't here last Thursday. So here's your initial value problem. Now, that function is continuous on minus infinity to infinity. The trouble is, it's not integrable, okay? We don't have a technique that will do that, okay? Now, I've written it this way. They do it slightly differently, okay? And I don't know why. But what they do, what I would say do is integrate. Well, I don't need to do it down here. I'm going to do it up here. Integrate both sides. And this will be let's just call it y for now, is equal to, but this one, you cannot integrate that integrand. There is no way to do it except numerically. So what we do, we integrate, change the variable e to the minus t squared dt. This is going to be some function of x, so you'll have an x of 0 down here and an x up here. Okay? Yes?
So we do ln, cancel out that e.
Okay. Oh, okay, let's try it. What would it be? You think the antiderivative will be ln of what?
Be like, you have to do ln of y. I mean, you have to set both sides equal to ln, right?
Okay.
That e.
So you're going to take the ln of both sides
Well, for you,
before you do the integration. Is that what you mean? So you're doing an ln of a dy?
well, I mean, you would have to do ln of dy, right?
Yeah, but I don't even know
Or you can
what
do
that
ln
means.
of y.
No, you have to do it both sides. That's not a y, that's a dy.
I know, but then to go to the next step and do ln. I don't know.
Oh, no, down here. No, you've already got the integrals in place. Okay. No, try it to your heart's content. You're not going to get an answer. Okay. So, I'm going to erase that, okay, to keep from confusing somebody else, okay? It's not integrable. Take my word for it, okay? But it's something pretty close to something y'all are pretty familiar with. Have you ever heard of a bell curve? You've lived by that, a bell curve?
Yeah.
This basically is what this is. This isn't normalized, so it's not a normal curve, bell curve, but this has that shape. And that is a smooth, continuous function for all things, but it's just not integrable, okay? But what you can do, we know this is true, and when y of 3 is equal to 5, and that's equal to the integral from 3 to x e to the minus t squared dt. Well, so that means that your y of x they've written this rather strangely, but this is what it winds up to. Y of 3, and why they don't go on and say what y of 3 is, it's 5 plus the integral from 3 to x e to the minus t squared dt, and this will be y of x is equal to 5 plus the integral 3 to x of e to the minus t squared dt. Now, why they took so long to say that, but that is your answer. I mean, there's nothing else you can do except numerically integrate. And if you have a package and you can do it, plug in an x, you plug in that here, you integrate that. I mean, you do a numerical integration up to whatever value you put in there, and that'll be your solution. Okay. So it seems like you could write them all down that way, but no, if you can integrate it, integrate it. That one you can't, so you just leave it there. So for some reason I thought, why did they even bother with saying that? But they'd said it, so it's sad. Homework exercises here. Do any of the odds 1 through 21. There's a whole passel of them there. Most of those, I think the answers are in the back of the book, so do as many of those as it takes for you to feel comfortable about. Then do any of the odds that are in the back of the book, 23 through 27. And then do 29, if that's in the back, I think it is. Then either 31 or 33, if those are in the back, do those. You can see if 35 is back there. I think it might be. Then number 37 goes back to problem strange, 21 and then 22. I would just do 21 probably, okay? I don't know why they're... Oh, looking for a singular solution, okay? Then do, if they're in the back of the book, either 39 or 41. I think you can do 43 if it's in the back of the book. And then any of the odds 45 to 49 if they're in the back. Now, most of the time the discussion problems are not back there, but if any of them are, you can take a look at those and go with it. Okay. So those were your separable. They are usually rather straightforward, usually sort of fun to do, usually solvable because they're separable, unless you want into one of those integrals you can't do, and then leave it in integral form. So let's go to a new class, not separable, but, and this is a little bizarre, they just call them linear equations. Well, That was a whole class of equations, linear equations. And basically this whole class you can do this way. If they're not separable, then here's a new technique. So let me clear this out of the way, and we'll introduce what we mean by a linear equation. So, first order differential equations, we're going to look at some linear differential equations. They say they're especially friendly family of equations in that given a linear expression, whether first order or higher order, always a good possibility you can find some sort of solution. So the form of a linear first order differential equation was first given back in section 1.1, and basically here's what you have. First order differential equation of the form a1 of x dy dx plus a0 of x y is equal to some g of x. Okay? Now, these a's here are what I call your coefficient functions. Okay? What I mean by that is the coefficient of your y terms, y and dy, derivative of y. But they're not pure number coefficients. They can be any function of your independent variable x. Okay? And if you remember back earlier, you could just string a whole bunch of these together. A sub n of x, the nth derivative of y with respect to x to the n, plus you went all down until these are your last two. And so since we're only doing linear, we're going to not have the second derivatives, third derivatives, fourth derivatives, any of those. We just have these. And that's for the a sub 1. It means that's the one for the first derivative. A sub 0 is the one for the zeroth derivative, which means y itself. And then you have g of x. So that's the generic form of a first order ordinary linear differential equation. Okay. Now, as you might guess, okay, these may not be separable. Okay. Because if you try to divide out this one, you may still have it here. Try to divide out this one, it'll still be here. These may not be separable. And even though they're not, we're going to do something to it that sounds like we're trying to make them separable. First thing we're going to do is divide everything by a1 of x. Okay? This obviously goes away. So you have dy dx plus. Now, a1 is a function, a0 is a function of x, a1 is a function of x, so the quotient function is a function of x. Let's just give it a new name, p of x. Okay? Why p of x? Don't know, but they're going to use it forever. Okay? So that's what your p of x is, times y, and this is equal to some f of x. Okay? Y f of x, it doesn't matter. G of x is a function of x, a1 of x is a function of x, so the quotient is a function of x. Let's give it a new name, f of x. Now this is going to be what we're going to refer to as, from now on, our standard form of a linear first order differential equation. Okay? We're not going to have the coefficient of the coefficient function of your first derivative being some a of x. We're going to divide it out so you just have a naked dy dx. Okay? Just that by itself. Okay. Now, here are some equations, and you tell me if they're linear or not. Dy dx is equal to plus 2xy equals 0. Is that a linear equation or not?
Yeah.
Yes, Yes, it is. Because this is to the first power, that y is to the first power. Your f of x is 0, nothing wrong with that. Your p of x is 2x. Perfectly fine. Perfectly fine. Okay? How about this one? dy dx is equal to y plus 5.
Yes.
Yes, because all you have to do is subtract the y from both sides, and you have dy dx minus y is equal to 5. So your p of x is just minus 1, and your f of x is 5. Perfectly fine. Okay? Now, here's something that's sort of important here. These are linear functions, but I miswrote this, so it's ugly. Okay. But these are both separable. So what we're going to do in this section, I would not even mess with it as a linear function, because you see you can subtract 2xy from both sides here, write it in differential form, and then divide by the y, and you have a separable equation. You have dy over y is equal to 2x dx. Separable, don't do anything we're going to do with this one. Okay? How about this one? Yeah, write it in differential form. dy is equal to y plus 5 times dx. Divide by y plus 5. You have all your y's over here, dx over here. Separable. Don't do anything. Even though that is a perfectly linear thing, and everything we're going to do from now on will work, if you can separate them, separate them. Okay? And that one is, I wrote it that way, but you don't need to. You wouldn't want to do that. Write it as that. But how about this one? Whoops. For some reason, my pen gave out. Let's get it back. Okay, here we go. How about this one? Looks very similar. dy dx plus y equal x. Certainly a linear, very simple. Okay? Your p of x is 1. Your f of x is x. Okay? But can you separate those?
It's already separated.
Okay, it looks like it is, but you can't, if you wrote it, okay, before you could write it in differential form, you'd have to subtract a y from both sides, right? And then you have dy dx is equal to x minus y. Then write it in differential form, dy is equal to x minus y dx. Uh-oh, SpaghettiOs, we got a problem. You can't get the y over here because that's subtracted, not multiplied. This was okay because that was a 0 here. You can move that whole term over there. It's multiplied. This was okay because it was a constant over there. In fact, you wouldn't even want to do that. Leave it in this form. Divide by this and put the dx over there. You're perfectly happy. This way, because of that plus sign there, ultimately came to plus and minus here, you can't separate it. You can only separate multiplications and division, not additions.
Could you separate it if it was a partial derivative?
Partial derivative?
Could you separate it then?
Don't think it'd be an ordinary linear first order differential equation then, would it? Yeah. I don't think so. Okay. I'm not even sure you could otherwise, but I know it wouldn't fit the bill then. So, what they're going to do is launch into how you go about solving these things. Okay? If you can't separate this linear, ordinary, first order differential equation, then write it in the standard form, which is this form right here, and then we proceed with trying to solve it. Now again, they introduce so many new functions and do all sorts of weird things with it. This gets really confusing. You just have to try to keep vision of the forest and not get lost in the trees, okay? Because it's easy to do. So let me start with a clean sheet here. And I will guarantee you we are not going to have time to finish this, but let's at least get started. Okay? So here's your dy dx plus p of x y equal f of x. There's your function. Okay? That's your first order, ordinary, linear differential equation in standard form. Coefficient 1 here, coefficient p of x here, f of x here. And with the caveat, this is not separable. If it is separable, the thing will still work, but you don't even want to mess with it if it's separable. If it's separable, separate it and do it that way. If it's not, though, then here's the procedure. Okay. Now, okay. I'll read you what they say, and honestly, to me, it feels like you get the cart before the horse, and you're not even sure you got a horse. So let me see. The method for solving this equation hinges on a remarkable fact that the left-hand side of the equation can be recast into the form of an exact derivative of a product by multiplying both sides of that equation by a special function mu of x. So we're going to multiply everything by mu of x, okay? And that's a very special function, okay? It says it's relatively easy to find the function mu of x because of what we know we want it to be, okay? Now, they stop right there and go into la-la land, okay? That's my only description of what they're doing here. And for no reason at all, they do this. Okay. They're going to take the function y and multiply it by the mu of x. Okay? Now, here the y, you're taking a derivative. So let's multiply by mu of x. So this will be d by dx of, not y anymore, but mu of x times y. Okay? Now, that's all they've done. They've taken the y from here and multiplied by mu of x. Okay? Now, then the first statement there, dy dx becomes this, right? Because now you're multiplying by mu of x. Well, that's a product rule. And the product rule tells you, let me get it in the right order, it's the first mu of x times dy dx, derivative of the second, plus y times d mu dx. Okay? They put d mu dx y. Okay? Now, this, you see, is just simply this thing multiplied by mu of x. Right? Now, if you let this be that, so in other words, this term you've just multiplied mu of x, here you want this to be, there's your y, you want the d mu dx to equal your p of x. Okay? That's what you except if you multiply this by mu, you have to multiply. So this is mu times p of x. Okay, sorry about that. Du dx has to be mu times p of x. Okay. Because if this is times mu of x, you need that to be times mu of x as well. Okay? We're not worrying about the right-hand side at all. We're just worrying with the left-hand side. Okay. Now this statement here, d mu dx is equal to mu times p of x. Okay? Now, what we're going to do is separate that equation. Make this d mu over mu, divide both sides by mu, and write it in differential form, is equal to p of x dx. Okay? How much time we got? Just a couple minutes?
3 minutes.
3 minutes. Let's see what we can do. We know this is going to be log mu is equal to p of x dx, right? Well, let's undo the log by doing an e. Okay? So this will be mu is equal to e to the p of x dx. Okay? That's what our special function mu is. I think I left off an integral there. Yes, I did. Because when you integrate this. So this is the integral of p. So that's what we got. So mu of x is e to the integral of p of x dx. That's your special function, mu, that you're going to multiply everything by. Okay. Now, how does it seem like... Oh, I turned 2 pages. Sorry about that. Okay. That is called your integrating factor. Okay? And I think that's probably where we're going to stop right here. That is your integrating factor. And I forgot to bring up my eraser, so I'm going to have to use this lousy one. Oh, it doesn't do too bad a job. We have your integrating factor. Mu of x is equal to the integral of e to the, is equal to e to the integral of p of x dx. Okay? Now, basically, what they do next, to me, gets really confusing. But they say do not memorize it, just do the stuff. So basically, we may just jump down and start at the box at the bottom. But we'll do a quick review and go from there. I don't think we may have done, no, we haven't done enough for any new homework exercises here. So this will be it for today. So we started in 2.2 and wound up in 2.3, right? I believe that's right. Yeah, we started in 2.2 and wound up in 2.3. Good deal. Any questions? All right, glad y'all made it today. Keep working on the test. Like I said, I've got 1 in. I've only got 1 paper in so far, too. Keep working on that. And for those of you in other classes, remember you have tests in those classes as well, right?
Cal 3?
Yeah.
Do you have the test?
Yeah. Oh, you never got it?
No.
Okay, yeah. We just finished it last time. Okay. I'll have to go down to my office and get it. Do you have a minute?
Yeah.
After class, okay. All right. Let's have another test come in. That's good to see. Let me, before I lose it.
Yeah.
All right. Good deal. Okay, let me get this saved.